All right, we're ready for section 10.3. We are going to start looking at simplifying radicals and also the distance formula. And I think the Pythagorean theorem shows up in this section. And the circles, we're actually not going to do circles. All right, but we'll talk about the rest of these things. So the first topic here is multiplying radicals here. So if you have the same root, square root, and you're asked to multiply two square roots, you can actually multiply everything inside and put it underneath the radical. So we can take 7 times 6, which is 42, right? And so we can write this as the square root of 42. And then there's an x and a t, so x times t, so 42xt. Another thing to think about when you have a radical like this, you want to see if there are any perfect square factors of 42. So are there any perfect square factors of 42? It's a good question. I don't think so. The factors of 42 are 1 and 42, 2 and 21. Those aren't perfect squares. 3 and something. 3 and something. 3 goes into 42. Let's see. 14 times. 3 and 14. No, that doesn't work either. 4 doesn't go into 42. 5 doesn't. 6 doesn't. So 6 and 7, right? But none of those are perfect squares. So this is as simplified as we can get. Square root 42xt. So we can combine the radicals. All right. Let's look at the next one. We have two fifth roots, right? So let's multiply these things together. We can have the fifth root of the product of all of this stuff. So 6 times 4 is 24. R squared times R squared is R to the fourth. And T cubed times T is T to the fourth. All right, and there's nothing else we can do with that. That is the fifth root of 24, R to the fourth, T to the fourth, and that's it. This next one's a little different. You have a square root and a cube root. If you have a square root and a cube root, guess what? Nothing we can do with that. We can't multiply two different roots together, so it is already simplified. Square root of 3 times cube root of 7. Can't do anything else with that. All right, let's look at the next thing. We have the cube root of a quotient here. If you have the cube root of a quotient, you can take the cube root of both the top and the bottom separately. So here I could take the cube root of 27 over the cube root of 8. All right. So 27 is a perfect cube, right? Because 3 times 3 times 3 is 27, so cube root of 27 is 3. 2 times 2 times 2 is 8, so the cube root of 8 is 2. And then we get 3 halves. The next one, we have the fifth root of 7x over 32. So we could write that as the fifth root of 7x over the fifth root of 32. Now, there's nothing we can do at the top. 7 is not a perfect fifth root. But the bottom, the fifth root of 32, and you could use your calculator to find that, or you could just, 2 times itself 5 times is 32. So the fifth root of 32 is 2. And so the top we don't do anything with, but the bottom we can. So we get the fifth root of 7x over 2. Fifth root of 7x over 2. And let's look at this last one here, the cube root of x to the 9th over 216. Let's see. And it's a negative, right? You can take the cube root of a negative. In fact, any odd root you can take of a negative. Even roots you cannot take of a negative, but we can take the cube root of a negative. Let's see. So we could write this as, in the negative, you could apply either to the top or the bottom, whichever one you prefer. Maybe I'll put it with the bottom since it's a number, it might be easier. So we could write this as the cube root of x to the 9th over the cube root of negative 216. Again, when the negative is in front of the fraction bar, I could put the negative at the top or the bottom. It does not matter. Or you could leave the negative out front here if you liked. But let's do this problem then. The cube root of x to the ninth. So what times itself 3 times would give you x to the ninth? Well, if you go back to your fractional powers, that might help. The cube root is the same as the 1/3 power, right? So x to the ninth to the 1/3, that's pretty easy. 9 times, you take a power to a power, you multiply the exponents. That would give us 9 times a third, which is be x cubed on the top. So we'll get there. Eventually, we're going to have an x cubed on the top. On the bottom, though, we have this cube root of negative 216. So what times itself, and you could use your calculator to find this, what times itself 3 times gives you 216. Oh, I don't have my calculator on me, so that's terrible, but I think it was 8 times 8 is 64. Does that work? Does 8 work? No, I don't think so. Or does it work? Times 4 is 32. No, that doesn't work. 8 times 8 times 8, that doesn't work, does it? So let's think about this for a second. What times itself, is there anything times itself 3 times to give you negative 216? Maybe I'll use a calculator to help me out. I don't know. Let's see. I'm going to try to use my calculator on my computer and see if it helps. Or maybe, let's see. Oh, 6 works, right? 6 works. Okay. So the cube root of negative 216 is actually negative 6. So we get x cubed over negative 6. Whew, that was close. I almost didn't know that one. But we got it. All right. So then we go to these ones at the bottom here. We're asked to simplify these radicals. All right. I like to use fractional powers when we run into problems like this. So we have x to the 28th and the 42nd root of that. So what I like to do, again, is use the rational exponents. We could write this as x to the 28th raised to the 1 over 42 power, right? So multiplying 28 times 1 over 42, that becomes x to the 28 over 42 power. All right, so this fraction, can we reduce it? I think 7 goes into both of those, right? 7 goes into 28 4 times. And 7 goes into 42 6 times. Oh, we can reduce that more, right? 2 goes into 4 twice. And into 6 3 times. So we get x to the 2/3, and that would be an okay answer. But we could also write this as in radical form, right? This means we take x squared and we have the cube root. So we could write this as the cube root of x squared. So this would be probably the preferred answer, but x to the 2/3 should work also. You might check on MyLab if you run into a question like that and see if they accept rational exponents. And they'll usually tell you if they want a radical or rational exponent. So they don't tell you, they'll probably accept both. All right, let's look at this next one. We have all this stuff and the square root of all this stuff, right? So we could write this as the 1/2 power. And so we could take all this stuff, 8x cubed, y to the 6th, z to the 11th, all to the 1/2 power. Now some of this will be kind of nice. So we have 8 to the 1/2 power, but you know what? The square root of 8 is not a nice number. So what I might do is kind of factor something out of 8 that is a perfect square, like 4, right? So I'm going to write 8 as 2 times 4. And the reason I did that again is because 4 is a perfect square. Okay. X cubed, I'm going to write as x squared times x. Because x squared is a perfect square. Y to the sixth, I'm going to write as y. Oh, y to the sixth is already a perfect square. I'm just going to leave it, right? And z to the 11th, I'm going to write as z to the 10th times z. Now, the reason I did all that, and I still have this 1/2 power, the reason I did all that is I wanted to get things that were even powers of either a variable or a number. Like 4 squared is, or 2 squared is 4, right? X squared is x squared. Y cubed squared would be y to the 6th. Z to the 5th squared would be z to the 10th. So we can simplify this, all right? 2, that's not going to help us any, so I'm going to write, let's see, square root of 2, right? 1/2, 2 to the 1/2 is the square root of 2. But 4 to the 1/2 is actually 2. So square root of 2 times 2. X squared to the 1/2 is just x times x. X to the 1/2 is the square root of x. Y to the 6th to the 1/2 would be y cubed. Z to the 10th to the 1/2 would be z to the 5th. And z to the 1/2 is the square root of z. All right, now we can put this all together. In fact, let's try to do that. So I'm going to take all the stuff that doesn't have radicals, the 2, the x, the y cubed, the z to the 5th. I'm going to write all those down. So 2x y cubed z to the 5th. So I took care of the 2, the x, y cubed, the z to the 5th. What we have left is the square root of 2, square root of x, and square root of z. And they're all multiplied together, so we can write this times the square root of 2xz. And so the goal really is to get everything outside of the radical that we can, and we have accomplished that in this case. All right, so let's look at the next one and see if we can do something similar. All right, so cube root of all this stuff, right? So first thing I'm going to do is rewrite this. So 1250, a to the 5th, b to the 7th, to the 1/3 power. So now what I want to do is try to take out perfect cube factors from all these things. Okay. You may look at this 1250 and say, well, 125 is a factor of 1250, and 125 is a perfect cube. So what I'm going to do is I'm going to write this as 125 times 10. The reason I did that is I recognize that 125 is a perfect cube. You might not know that, but you can try to find factors. You could say, well, what goes into 1250 that might be a perfect cube? And look at several different possibilities. 10 is not, but 50 goes into that, 50 is not. So you could, 25 is, but then there's a bigger one. You want to find the largest perfect cube that you can take out, and it happens to be 125. So perfect cube that goes into a to the 5th, well, a cubed, right? So I'm going to rewrite a to the 5th as a cubed times a squared. And again, the reason I did that is a cubed is a perfect cube. B to the 7th, I'm going to write as b. Now I could write b cubed times b to the 4th, but there's a larger perfect cube, b to the 6th, right? 3 will go into 6, won't it? So b to the 6th times b can replace the b to the 7th. So we'll take all this to the 1/3 power. Let's see what that gives us. Let's see, the cube root of 125, or 125 to the 1/3, would just be 5. 10 to the 1/3 is the cube root of 10. A cubed to the 1/3 is just a. A squared to the 1/3 is the cube root of a squared. B to the 6th to the 1/3 would be b squared. And b to the 1/3 is the cube root of b. All right, so what do we have? Let's take all the things that don't have a cube root, the 5, the a, and the b squared. I'll write those down first. So 5 times a times b squared. So I got rid of the 5, the a, the b squared. Let's see what we have left. Cube root of 10, cube root of a squared, cube root of b. So then I can write times the cube root of the product of all those things, 10a squared b. And that is simplified completely, and we can't really do anything else. We can't take a perfect cube out of 10 or a squared or b. All right, so that's it for this page. We'll continue. There's one more page for section 10.3. We'll continue with the next video.